Thank you, everybody, for coming. I'm Mark Kennedy. I work for Symantec. My colleague, Dr. Igor Muttik, works for McAfee. Kind of strange to see competitors doing a joint thing, but that's because we work in conjunction with the IEEE on quite a few cross-industry solutions trying to just better the ecosystem. So a little bit of information about who we are. IEEE runs something called the Industry Connection Security Group. Very many security companies take part in this. And then there are sub-working groups that run under that program. One of them is the Malware Working Group. And that's where this effort came from. And this effort, we call it the Clean File Metadata Exchange, or CMX. A little bit of background. As everyone knows, the malware problem is constantly growing. If you've seen a presentation from any AV company, they give you the graph with the number just going up exponentially. We're seeing an increase in both the quantity and the complexity of the attacks. They use a lot of evasion techniques, trying to avoid our signature scanners. And some of these are now the attacks are quite large, and they use a lot of high-level languages and other obfuscation. So that leads us to need to develop better heuristics. Heuristics are important because they can detect threats ahead of time, but the other side of good heuristics are the problem of false positives. And actually, I think a number of the companies, as we're working on these heuristics, solving the false positive problem is a harder challenge than solving the malware detection problem. And if there are too many false positives, that annoys the customers and makes them turn the technology off. So we have to hit that right balance where they're willing to suffer a few false positives to get better protection, so we need to manage our false positives. So what are the issues with whitelists? Well, they're difficult to collect. You have to go around the web looking for websites or FTP sites that contain the software and pull it down. You have to make sure that what you're pulling down is real and hasn't already been Trojanized or otherwise infected. And some of the sources might actually be operated by malware authors just trying to fool us into whitelisting their malicious apps. This also introduces a delay between the software being published and it showing up in whitelists, which means if you go and you're one of the first people to pull down the new copy of Firefox, maybe the whitelisting companies haven't pulled that down, processed it through their system yet, and released it to the security companies. There are certain programs that are intrinsically variable, so they get modified as they go on disk, so they don't really are not well suited to whitelisting. And whitelists are a black and white classification. We don't really have a category within the whitelist to indicate that something is grayware. And legitimate software can be misused. In addition to that, some trusted software might have some backdoor functionality, Easter eggs, that could potentially be leveraged, though they're not exactly all what you want to be running. So the current approaches. On-machine whitelists, they've existed for years. All the security companies, where we've generated signatures that have false positives on them, we have to generate whitelists. Those go on the disk so that the detection is blocked. Some companies use it on-disk whitelist for things like tripwire and things that are looking for just modifications. Cloud whitelists, those are relatively new, where instead of maintaining all this, when you see a new file on the disk, you look it up in the cloud to see what is known about it. And this is where CMX really comes into play and can help tremendously. Right now, the vendors have to seek out the clean files. So security company A is out scrubbing looking for clean files. Security company B is out scrubbing for clean files. In some cases, we've worked out individual agreements with certain software publishers to get access to their files and their metadata, but that means they have to have a similar agreement in place for every security vendor that they want to try to interact with, which puts an extra burden on them. So CMX provides a single point of contact for software producers where they can submit their data and get it distributed out to all the different security vendors who are subscribing to it, one-to-one interaction. And this simplifies the exchange for both parties.
Okay, let me describe to you what CMX system actually is. CMX piggybacks on the metadata standard that IEEE malware working group developed a few years ago called Metadata for malware sharing standard. And it uses the same type of XML which is mostly populated with hashes of all the interesting files. And because majority of malware is distributed in PE and DLL format in these days for Win32 platform, majority of heuristics that Mark talked about are focused on these types of objects. So metadata for clean files is also focused on similar objects because clean whitelist is the safety net to prevent false positives on this type of software. We are currently interested in collecting clean metadata predominantly for Windows files and also installers for these files. So that would cover formats like CAB, MSI, and we are only interested in metadata for files which are publicly released. I mean, there are all sorts of internal builds of software. These are also clean, but there is no reason to collect this type of data for these files because they are not in public circulation, so their exposure to security products, antivirus products is very limited. So what type of metadata we actually gather? We compute hashes for all the elements of the installers of P and DLL files in particular. That's all the historical hashes like MD5, SHA-1, SHA-256, and in future we are going to expand it with more modern hashes, including even SHA-3. We are also interested in file names, the name as it will appear after the object is installed on the end user computer. That includes the path name where it installs itself, like with the example with Firefox, that would be program files, Mozilla, and then Firefox folder. These paths would be normalized and obviously would handle all the Unicode conversions of the characters. For Win32 executables, they carry a lot of information and resources, and that information includes the vendor which created that file. They are frequently digitally signed, and all these extractions are useful for the purpose of assessing the quality of whitelisting, and they're relevant for assigning certain level of trust to all the elements of the whitelist. And that is also included in the XML that we circulate within the CMX system, as well as file version information, which is also for Win32 binaries is included in the resources. So this slide shows the actual example of what's being shared. That's an example XML following the header, which contains standard XML declarations, the source, the name of the author, the originator of that data, the comments about it, and in this case, comment just tells you that this XML complies with the MMDF malware metadata exchange format previously developed by IEEE, and it also has a UTC timestamp when that piece of metadata was compiled. And then most importantly, it contains a block of hashes, all the hashes that our extraction tool can generate, and file names, file folders, and the information of what package this software belongs to. So obviously, the XML is not a very efficient way of transmitting data. So what we do to minimize the bandwidth in transmitting these files, we actually zip them up and upload to the server. So that saves on the bandwidth and also ensures that the integrity of the file can be verified through checking the validity of the zip file. So why do we share XMLs and why don't we share actual files? Actual files would actually be useful because when we look at the clean file and when we verify that certain heuristic falses on it, we can take steps, change our scripts, change our development procedures and fix the problem at the source where the heuristic is actually being developed. But not in all cases clean files are available to us. One situation is, for example, when big corporations use their internal binaries, internal tools, which are just existing on their network, not anywhere else. So these files are not available to us, and in many cases, companies are not very willing to share them outside of their environment. Another reason is that sharing clean files, and in particular sharing installation files, setups, is very likely a legal violation of the copyright. Because if many security companies start sharing installations for commercial software, it wouldn't look very kosher from the point of view of legal departments. Essentially, these commercial pieces of software will be transmitted from one place to another with no payments to the source companies. And it could potentially be a source of piracy. So we don't want to be involved in this type of activity. And also, when collecting clean files from commercial companies, these are paid for products and some are very expensive. So gathering clean files for commercial software is going to be a very expensive exercise. So a simpler way of handling that is just to collect hashes of these clean files, and that doesn't involve actually transmitting copyrighted binaries and installers. At the same time, obviously, it reduces the strain on the required storage and the bandwidth to transmit the data. But most importantly, transmitting hashes is actually sufficient for most of the technologies that are in use at antivirus companies. In majority of cases, all the heuristics, when they detect something, subsequently verify that the file is clean or not. And that verification can easily be done by just checking the hash of the file. So how the system actually works. Initially, we discussed various methods of creating some relational database, for example, and pouring data from all the sources, like software manufacturers and publishing houses, into this database. But that would be a very complex type of design, because we would have to be judges and mediators in deciding whose decision and whose classification of a particular file as clean or dirty, or if classification changes, whose decision is final. So we didn't want that complexity, so went for a fairly simplistic transactional log system, and each provider of the data, and that in most cases would be a publishing house, would just submit a zip with the metadata to the system, and consumers of that data would know what the source was, and the same file can actually appear in multiple submissions from multiple sources in principle. We generated Python-based tools to extract all the metadata necessary, and the XML that I showed you previously was actually created with these Python scripts. And providers of the data, all they need to do is just point these Python scripts to their builds, and the output is an XML file wrapped up into a zip, which can be directly uploaded to a portal provided by IEEE. That portal that we built has two modes of operation. The first mode is like a web interface where you can poke around and see what's in there and what folders and files were added to it. And another way of handling that interaction with the portal is through command line tools, because we want the whole operation actually to be automatable. The system now was built. It's operational. It sits on the servers provided by Avira, which is a German antivirus company. And the URL on this slide, IEEE-cmx.avira.com, is live. It should work. And if you open it, you would see a login screen. To be able to log into the system, you need an account. And these accounts can be created by IEEE. The system which we built is actually heavily based on previously created system for sharing malicious URLs called Mute. And it required just several small adjustments to make it work for sharing metadata for clean files. Okay, if you follow the URL, that's what you'll see. That's the login screen for IEEE CMX program. You punch in the login email, password, and log in. Then you would see the main menu, which is in the right bottom corner. And there are three simple buttons: submit metadata, manage metadata, and see statistics, which would basically show you who uploaded what, in what quantities, and on what time. The way we designed it is that each company interacting with the system has a super user, which is in charge of all the children account for this particular company. So if you take one company, there is one administrator within it who can create sub-accounts. Sub-accounts will be able to interact with the system, make uploads, downloads, and the super user can manage these sub-accounts. On this screenshot, you see the page which contains all the tools kept within the portal. That's all the downloads of documentation, the client for various platforms, Unix, Macintosh, API guide, which is a document describing how to interact with the portal via command line tools, the actual Python client, which can be executed on multiple platforms, obviously, if you install Python on them, and the guide to operate the system itself as a user. And that's probably the most interesting screenshot. It shows you the actual list of metadata submissions for a particular company. Because the company name is associated with each submission, consumers of the data, when they download, can associate their own level of trust to what they get. IEEE will do the vetting of companies who submit metadata, but we wanted each individual consumer of the data to be able to handle their own trust relationships individually, so that they can decide who to trust and who not to trust. And that transactional operation helps with this goal. So in the left column, you see the number of submission, the ID number of submission, then the company name, the username who was logged in when this submission was made, and then if you press on a particular icon on the very right, you would actually be able to download the zip containing an XML that I showed you before, something very similar. Normally, in day-to-day operation, there would be no need to interact with this system through the UI. You would almost always use command line tools, and the system would operate in automatic fashion. Okay, let me now pass the mic back to Mark, and he will describe to you the logistics.
So the system is designed, the way we've laid it out, that the cost to providers, third-party software developers, is going to be free. We want them submitting us their metadata. We want to lower the cost as much as possible, and there's not much lower than free. That we provide the tools to them, we'll provide them whatever support they need to be able to provide that data into the system, because that's very valuable to us. To the consumer, to primarily security companies, we're going to keep the cost at the bare minimum that we need to operate the system. So we need to cover the bandwidth cost for the submissions and the retrievals, the hardware cost for the systems that are maintaining the system, and the administrative costs. IEEE has overheads in being able to maintain a program like this, collecting funds and all the stuff there. We're not trying to make any profit on this. The whole point of this is to improve the overall ecosystem and not to make money for IEEE or make money for the security companies. So what are the takeaways we want for this presentation for you? If you are a software producer, you'll benefit from being a provider. You'll be contributing to the ecosystem and greatly reduce, if not eliminate, the possibility of getting false positives on your software. If you are an enterprise administrator, you'll benefit from being a provider, because you'll be able to submit just the metadata for your internal apps. You can build this into, the scripts can be built into your configuration management process, so the hashes are provided and false positives are reduced or eliminated. And you don't have to send us the actual software, we just need the metadata. And if you're a security company or an AV vendor, you benefit from being a consumer, because you have real-time access to this data. In many cases, if it's tied in correctly, you'll have the hash for a clean file before any consumer would ever see that file on their disk. So it reduces our cost because we don't have to go out searching for the files like we do now, and we get lower FP rates, which allows us to be more aggressive on the true positive side of the thing, of the house. We really want to thank the people from Avira. They donated their time and development resources in putting the system together for us and getting it set up. Especially Philip Wolf, who runs the overall program, and Thomas Weigel, who did the actual coding of the system. Any questions? Do you want to use the mic or talk loudly?
I can talk loud.
Okay.
So do you envision AV companies doing a routine pull of this in order to put it into their current cloud solutions for scalability issues?
Yes, the idea is the providers are pumping data into it as it comes in. The security companies are just constantly, or whatever interval they want, pulling what's new, what's new, what's new. And I guess one of the other key points in the system is the CMX does not do any correlation or any data processing at all. It's merely, here's new stuff that's come in, here's the stuff that's new for you since the last time you asked, here's a different set of new stuff for the next guy that he asked. All correlation and other kind of processing is done by the clients. It's up to them to figure out how they want to use this data. Yes, sir.
Is there any sort of revocation list where you
yes.
say this was falsely published as clean?
Yes. One of the records that can come in can be a revocation of it. This file, this hash is not to be trusted, and then that will get pushed out in the same. It comes in the same feed, it'll go out in the same feed. We're also working on building in some security systems in the way the actual submission is done to make sure that we're not being spoofed. I mean, I guess it'd be a sign of acceptance in the community if the bad guys decide they want to attack our system. But we're taking steps to prevent that. Yes, sir.
Does this correlate to IEEE SWID tags, and would I expect to see this kind of information correlated in the future with CWD or SCAP data?
Looks like we don't know.
The first part, IEEE has SWID tags today. There's a standard out for that. So
their software ID, I'm assuming that's what it stands for? I'm not familiar with it.
And you mentioned packet capture data. This is only file-based.
Not packet capture, but for SCAT data results back from sensors that would correlate to these results. So if I take an inventory of an asset and I look at what software's on it, and I want to correlate that to known patterns.
Right. Now, you would have to be a subscriber, get this data, and do the matching up yourself. The system is not queryable for anything, any specific data. It's just a conduit for providing the data out to the subscribers, and then the subscribers build the systems on top of that. Yes, sir.
Yeah, was there any consideration, since you're already dealing in the majority of PE formatted files, of doing hashes of just sections for better granularity for false positives? I'm given the example case of somebody on maybe the resources section for a different language, but it's still the same executable, but it's whole private hash, or its whole hash is completely different.
I hadn't directly considered that, but the system is certainly extensible to be able to handle something like that, although I'm not sure about the security vendors' cloud solutions and how they'd be able to deal with that. We're being given the hook by our proctor. Igor and I will be, well, we're going to attend the next session, and then we'll be available for questions immediately following the next section outside. Thank you very much.